let's get started. Good evening, everyone. My name is Christoph Innocentes. I'm the current Vice President of the Notre Dame Club of Washington, D.C. And I'm excited to welcome you to the first installment of Domers in STEM. For those of you who don't know, STEM stands for Science, Technology, Engineering, and Mathematics. And tonight we have a very special guest with us, Mr. Tom Harkins, Notre Dame class of '08, who is currently working with NASA on the James Webb Space Telescope, the JWST, which is slated to replace the Hubble telescope later this year. I think the launch date is October 31st, 2021. And yeah, so without further ado, let's hear from Tom himself. Take it away.
All right, so as Christoph said, I'm Tom Harkins. I'm here to talk to you about the James Webb Space Telescope. I'm a flight operations engineer on the project, and it's going to be launching later this year. October 2021 is our launch date. So briefly, a little bit about me. So I grew up and went to school outside of Boston, Massachusetts. And we'll leave some time, just to mention, we'll leave some time for Q&A at the end. So feel free to save up those questions. So a little about me. I grew up and went to school outside of Boston, Massachusetts. Hobbies, although I have 2 young kids, so I don't have much time lately. And if you hear them yelling in the background, that's no charge. Hobbies are reading, board games, and jujitsu, though it's been a while, sadly, for that last one, since before COVID. So yeah, as Christoph mentioned, I went to Notre Dame undergrad, bachelor's in aerospace engineering in 2008. And then I turned over to the dark side for my master's, got astronautical in 2012. And that was through my company, Northrop Grumman. For me, to talk a little bit about the STEM path that I followed, engineering was always a natural fit, trying to figure out how things worked. Tinkering with Legos, the classic story. It was never really a hard decision for me what to study. Engineering was a natural fit. So at Notre Dame, I did research as an undergrad at the Hessert Aerospace Laboratory right there on campus. And then senior year, I interned at Pratt & Whitney in Hartford, Connecticut, doing fluid dynamics on aircraft engines. So, and then after graduation, I moved over to Northrop Grumman. I've actually been there ever since. And that has taken me all around the country. Started out supporting launches out of Cape Canaveral Kennedy Space Center in Florida. And that morphed into operations, so more so on the back end of what happens after launch. And that took me back to Florida in some places, and then also California, where the satellite that I'm going to talk to you about today, where it is now, where it lives, where it's getting built. And then I currently live in Maryland, and that's where our kind of project is headquartered, and our operations center is up in Baltimore. So I split my time there. Okay. So our project manager calls this the Webb by the numbers presentation. So you're gonna see the theme here. So the first number is 13,500,000,000. So 13.5 billion. And that's how far back in time Webb will look. Quite literally, it is looking back in time. So the mission goals of Webb, and you may hear me refer to it as Webb or JWST, or the observatory or the spacecraft. For our purposes, those are all equivalent. So the mission goals are fourfold. One is identifying the first light, or the end of the cosmic dark ages, which you see there, occurred about 13.7 billion years ago, very close to the Big Bang. The second is looking at the birthplace of stars and planets. The third is looking at the assembly and formation of galaxies. And the fourth is looking at planets and solar systems and the beginning of life. So there are other missions that specialize in planet hunting, but Webb can assist in that search. And what that means is looking in the habitable region around different stars. So Earth is a certain distance from our star, the sun, and that allows liquid water to exist on the surface. So what we know are the conditions for organic life is what Webb is going to look for in other solar systems to kind of lay the groundwork for future specialized missions that can search more closely. The other thing that it can do is look for different wavelengths of light within the atmospheres of those interesting planets, and actually tell what the composition is in terms of H2O, carbon dioxide, methane, things like that we know contribute to life as we know it. So as I said, Webb is quite literally a cosmic time machine. It is the most powerful and complex space telescope ever built. So the analogy to looking back in time is the light from the sun. I think it's known that it takes about 8 minutes to reach the Earth from the sun. So if you were to look up at the sun, hopefully not for a long period of time, you'd be seeing the sun as it was 8 minutes ago. So you are looking back in time, and these objects are 13.5 billion plus light years away. So that's how far back in time we're looking. Let's see. So I'm going to make a lot of comparisons to Hubble in this presentation. The first one here is that the light that Webb is looking at, is so far away that it's actually shifted in the electromagnetic spectrum towards the infrared, whereas Hubble looks in the visible part of the spectrum, so it can see what the naked eye can see, no different than looking up at the night sky. Webb can see in the infrared, and so the other advantage of that is that it can look through dust clouds, things that would get in the way of a simple human eye observation or an observation by Hubble. Webb can peer right through dust clouds and other things that might be in the way. So some of you might be familiar with a famous image that's called the Hubble Deep Field. If you're not familiar with it, I highly recommend you look it up, print it out, frame it, hang it in your living room. It's an amazing photograph. And the comparison to this that I'll continue throughout the presentation is that the Hubble Deep Field, what it is, the concept behind it was to look at an area of the night sky that was previously thought to be essentially blank. So if you were to hold up a soda straw in front of your eye, that's about the size of the portion of the sky that we're talking about. And it was, again, considered to be mostly blank until scientists devised an experiment or an image to take with Hubble. So every time it came around its orbit, it would stare at this one point in the sky over dozens and hundreds of orbits. And over time, it basically produced a long exposure image of this area of the night sky. And it turned out to have over 10,000 galaxies in it. So in a point of the sky that was thought to be blank with the naked eye, you can find 10,000 galaxies. And so Webb is gonna extrapolate on that 100-fold and look even closer at those things. So let's see, I'm gonna try to play an animation here. We tested it and hopefully it'll work for you. It's just gonna give you a little size comparison between the Hubble and Webb. Can you see that okay?
Yep.
I'll play it one more time. It's short. There's a person in there. There's no audio. There's a person in there too for physical size comparison. So Webb has about 6 times the collecting surface and is about 100 times more powerful than the Hubble. And the last thing I'll say, this is kind of my science spiel. If you're saving up some really hard science questions, please don't. I'm just an engineer. I'm not an astronomer. So let's see. All right, next chart. 1,500,000, so 1.5 million. So that's how far away from the Earth in kilometers Webb will orbit. We orbit at a place called Lagrange point 2, or L2 for short. And it's about 4 times the distance past the moon. You can see the orbit of Hubble here as well for comparison. Hubble orbits in low Earth orbit, which is the same orbit as the International Space Station, where the astronauts work. So another comparison here is, if you folks recall, there was an anomaly early on in the Hubble mission where its first images came out blurry, and it basically needed a pair of glasses, and it was successfully able to be corrected because, like I mentioned, it's in the same orbit where the astronauts work. So they were able to devise a mission and a piece of hardware that essentially, corrected its focus and gave it a new set of lenses, and it allowed it to take, the pictures that it's now famous for. So if it's not obvious from this picture, no one's coming to help the Webb telescope if there's an issue. No astronauts are coming out to L2. It's way too far away. And so what that means from an engineering perspective is we have to solve our own problems on board or from the ground through the sending commands and looking at telemetry data. We have to be able to solve those. And so that can be in the form of, if the ground is not in contact, the observatory has to take care of itself. It has to know what mode it's in, what mode it can go to safely, and what happened to get itself to that condition, and then sit in a safe attitude, both thermally and from a power standpoint, and then wait for the ground to come back and figure out what happened and how to get back to doing science. So one of the cool facts when I learned it was that, and I'll show you this in another animation, the point in space, the L2 point that Webb orbits, the size of that orbit around L2 is almost the same size as the distance that it is from the Earth. So if you picture it making this huge ellipse around this point in space, L2 is a stable point in space. We'll talk about why that point was chosen as part of the mission. So let me play another animation for you here. There's no sound on this one. So I'll play it one more time and point out a few things. So you can see that the Earth and the sun and the moon is in there too, if you look close. They stay on the same side of the observatory throughout the orbit. And that's what we call the hot side. I'm going to talk more about that next. So I have a little model here to help. So hopefully you can see this. Hold it this way. So here's the hot side of the observatory. Here's the sun, the Earth, and the moon. We have a big sun shield, this 5-layer passive cooling device that's going to protect the instruments that are up here that are going to do the science collecting, the imaging. So what that L2 orbit allows us to do is to keep those bright, thermally noisy objects in space on one side of the telescope. So they're always there away from the cold side. The other thing, if you can picture rotating this around, Webb can make a 360-degree turn, what we call in the yaw direction. with no issues with those bright objects moving in the sky. We have some constraints in the pitch direction. We have some constraints in the roll direction, but in the yaw direction, we're free to rotate 360 degrees at any time. And that goes back to the overall mission design, which allows us to look at 100% of the night sky over a 1-year period. So I'll talk a little bit more about the hot and the cold side next here. So minus 388 and positive 185. Those are the temperature extremes that the observatory is going to see. So the cold side, the observing side, is approximately minus 388 Fahrenheit, and that's pretty close to absolute zero. So we have the 5-layer sun shield here, excuse me, which is, for size comparison, it's about the size of a tennis court in this picture, fully deployed. And that's the passive cooling that dissipates the heat from those bright objects, the sun, the moon, and the earth, dissipates them so that the cold side is as close to absolute zero as we can get it. There's also some devices on board, or one main device that does active cooling. So as you can see, the primary mirror, as I mentioned, the secondary mirror, and the science instruments, the main mechanisms and equipment doing that science collection are on the cold side. Let's see, the hot side is near and dear to my heart. That's what I work on a day-to-day basis. The what we call it the spacecraft bus. In other words, it's basically the health and safety, the housekeeping, so to speak, functions of the observatory. So the computer, the attitude control hardware, the thrusters that help us get to the orbit, the communications antenna that's going to send data back and forth. So everything that keeps the observatory flying and well controlled is on the hot side. So as an aside, my specific role in the team has to do with managing and deploying and operating the communications antenna, which is the only link back and forth to planet Earth. So sending high rate science data as it's collected back down to Earth for storing and analysis and dissemination to the scientists all over the world who are going to make breakthrough discoveries with it. And then if and when we need to send commands up to the observatory to respond to contingencies, to do normal deployments, sequences, which we'll talk about more, things like that. So it's the two-way link back and forth to the Earth. And we use, in my picture at the beginning, if you saw me next to that satellite dish, that belongs to the Deep Space Network. We use their network of ground antennas, and they're located all over the world, and they actually communicate with all of the missions that are around our solar system. So I'm sure you saw in the news the Perseverance rover that landed on Mars a few weeks ago. They're sending data back and forth to Mars. They're also talking to Voyager, which is currently outside the solar system. So they do a lot of the heavy lifting for us. Let's see. So I talked about the sun shield and the cold side. One thing I'd like to pause here and just kind of zoom out a little bit on, this is what I think about as an engineer. When I look at this picture and I see, why does this machine, or a machine that looks like this, or how does it solve the mission goal that we talked about, which is to take long exposure images of distant objects in other galaxies throughout the universe. So one that we just talked about is the orbit, where that lends itself is, if you think about taking a long duration or a long exposure image with even your household camera, what do you have to do to get a good image? You have to stay really still, for one. So what are the sources of vibration or jitter that could occur to mess up an image? One would be thermal distortion. again, keeping those hot objects on one side. Another would be vibration caused by operation of the units that operate on the Webb telescope, inside the Webb telescope. So those are actually isolated. We have a deployable tower assembly, which isolates as much as possible the hot side from the cold side. So things like that. Basically, everything is centered around keeping us as still as possible so that we can sit and dwell for long periods of time looking at those distant objects. So one of the really cool things is that some of the objects Webb is going to look at are so far away that even something that's as big as Webb's primary mirror may only be receiving 1 photon per second from that light source. And so you can imagine, to build any sort of meaningful image of that thing, it's going to have to sit there for hours, days, weeks to put that together. So stability, thermal stability, and a quiet operation really drives all of our mission requirements. And hopefully now that's clear why. So 40 and 178. So up to now, we've talked about, or you've seen Webb in what we call the fully deployed state here in the bottom right. And what that means is the sun shield is unfurled, the 5-layer sun shield. The mirror backplane wings, we call them the primary mirror backplane wings. They open up, as you can see in the image there, like almost like ears on the side. They come out. And the reason for all of this, so the secondary mirror here swings out with a giant triangular boom. The reason for all of that is because no spacecraft this size can fit inside a rocket, not even a rocket that Elon Musk makes, unfortunately. So we have to do what's called a deployment. We have to, when I give this presentation to younger students, we call it a transformer, right? It has to mechanically reconfigure itself so that it can fit inside a rocket for launch and then unfurl itself to its operational state. So let me show you, let's see. Let me show you one other animation here. This will show you how it gets stowed inside the rocket. So again, for size comparison, trying to get a sense of how big that is when it's what we call fully stowed, sitting inside the payload fairing. It's about the size of a school bus, the dimensions wise, weighs about 14,000 pounds. So a little bit about our launch vehicle. We launch out of Kourou. It's in French Guiana, South America. Part of the reason for that is because the program is the Webb program is really a global collaboration between NASA, which does a lot of the engineering and management, and the European Space Agency, which owns the Ariane 5 rocket, launches out of there. We also have partners all over the world, universities helping with the science and a lot of the engineering development. Okay, so let's see. Christoph is going to provide a link to a deployments video. It's going to be a little too difficult to play it here. It's about 5 minutes long. It's my favorite thing. It's what my team works on. It's what we think about day in and day out. It's what we're going to be doing for the first several hours and days after launch is making sure that this sequence goes according to plan. without a hitch because no one is coming to the rescue. So we have to do all that from the ground. And what we do is we test and test and test, and we rehearse and rehearse. And I was just up in Baltimore earlier this week doing a launch simulation. It's no different than you've seen, in Apollo 13, talking over the headsets, and are we go for that operation, that type of thing. We script everything down to our communication, down to what we say on the nets. Everything is planned to a T. One of the things you'll see in that video, I'm just going to kind of talk to it here as I click through these slides. There, the next couple ones are similar. So here's the link in the presentation package as well. Is we do what's called a mid-course correction maneuver. So you could see it here. It's an animation of a thruster firing. So it's one of the only time critical maneuvers that we have to do during this sequence. The launch vehicle, unfortunately, doesn't give us enough velocity to get fully out to the L2 orbit. So we need to have some propellant on board, and we need to burn at the right attitude and the right duration to get ourselves out there. So that is our main focus, that and the other time critical deployment, which is our solar array, to give us enough power to operate all the units that have to do the work. So, let's see, so 40 deployable structures and 178 release devices. And just to reiterate what my team does is mostly what we do is we plan for contingencies. We plan how to respond when things don't go exactly right. We spent years doing it, and now we're at the point where we're sharpening the pencil. We're getting used to the ground system and the communications flow and reporting up through the various levels of management to make real-time decisions, because the time for planning is over. If something goes wrong, we have to execute. We have to be prepared to go. The decisions are made. So that's my presentation. So hopefully we've got some questions out there. I'd like to open it up. And again, don't ask me any hard science questions. I'll head off by saying one of the questions I get commonly is how long is Webb going to operate? So the mission design life is 5 or more years with a 10-year goal. Although if it's anything like Hubble, which we hope it will be, it'll be operating, much, much longer. And again, the size I mentioned, it's stowed. It's about the size of a school bus, 14,000 pounds, and then fully deployed, the sun shield is about the size of a tennis court. So with that, feel free to ask questions.
That was really awesome. Let's see. We have a question from my dad, I think.
Yes, you do. Thanks, Christoph. Hey, Tom, really amazing stuff. Really, really impressive and interesting. From a technology standpoint, the stuff that folks are doing at Grumman and NASA, of course, is always pretty impressive. And I know, there's a lot of talk with Webb on some of the spin-off technologies, like the wavefront sensing that's going to be used in medical, the pulse lasers, for the vibration, all those kind of things. And I'm going to apologize ahead of time because my question could certainly take another hour, and it's not the scientific side. I work in the space of manufacturing technology, and some of the transformative technologies that are going on now. Grumman is heavily into, and so is NASA. I'm just wondering, out in California over the past couple of years as they've been building this thing, how much have they been using things like additive and digital twin or AI, in actually putting this thing together and testing it out?
Yeah, so great question. So one of the challenges with space qualifying any piece of hardware, especially, I'll caveat this by saying, especially a mission like James Webb, where it's NASA's flagship mission, right? It was identified on the decadal survey as being, a heavy hitter for many scientists around the world that they wanted to have on orbit, is making sure that there's very low risk, right? So anything that gets put on James Webb, a program of this magnitude, $9 billion national asset, has to have been proven many times over to be reliable, operational in various, temperature regimes that are well outside anything they'll actually see on orbit. So even putting cameras on board to watch our deployments was a question mark for a long time. As far as I know, there are none on there, but I don't know everything about this program. So I guess I would say in general, it's the things you're looking at on this bird are lower tech than what you would see today. For example, our solid state recorder doesn't even have as much memory as your phone does. So things like that. So whereas there have been many technological advancements, like you mentioned, to get this thing off the ground. So one of the things is our primary mirror is gold-plated beryllium, and that was machined so finely that if I can recall off the top of my head, the analogy, if you were to extrapolate the smoothness of the surface of these mirrors over the size of the United States, of our country, the highest peak to valley would be 3 inches. So that's how precisely they're machined because of the job they have to do. So there have been opportunities for things like that. They also there were invented technologies of like the primary mirror, so they can change their shape in pitch and yaw and also radius of curvature. So you can change the point of focus of the actual surface of the mirror. So things like that. So I think maybe to answer your question in general, it's a mixed bag of low tech and high tech, if I could summarize.
No, great. Thanks.
Let's see. Ann Lewis is asking, when does it launch? You said October, but is there a specific date? I thought I saw somewhere online as like the 31st.
October 31st, 2021 is the scheduled date. Yeah.
Okay. Anyone else have a question here? Arthur?
Yeah, I have a question. This was a really interesting presentation, Tom. I do not have any remote. I'm not affiliated anyway in space. I just find this very interesting. But my question for you is, why did your project team choose that specific Lagrange point that's 1.5 million kilometers away? I'm guessing it's something to do with gravitational forces, but can you go into more detail on that?
Sure. So that goes back to what I was saying about keeping, I don't have a diagram of, there's 5 Lagrange points, and that L2 specifically is the one that keeps, I'll pull up my model here again, is the one that keeps the sun and the earth and the moon always on, basically in a line to the L2 point. So because James Webb is going to be doing, so much steady observing, it's going to want to keep those objects. So let me maybe as a point of comparison, compare it to Hubble. So if I think about the orbit of Hubble, which goes around the Earth every 90 minutes or so, is what happens in low Earth orbit. If you can picture, you're in the night sky half the day, and then the other half of the orbit, you're in the blinding sun. So every orbit, you're getting 45 minutes of sun, 45 minutes of darkness, and that temperature delta is stressing on hardware. It's predictable, but it's stressing. So the L2 point is stable in terms of the thermal characteristics of what we're looking for this mission, to keep those bright objects in one part of the sky.
Thank you. And how do you make sure that it will stay in that point, that it won't drift away?
Good question. So we have to do what's called a station keeping maneuver. And since it's orbiting a point in space, it's eventually, just like any, even a satellite in low Earth orbit, it's eventually going to be affected by gravity. And if you did nothing, it would burn up in the atmosphere. Well, at L2, it's going to orbit that point, but eventually it's going to drift out of that orbit. So I think it's every 3 weeks roughly, we have to do a maneuver to hold ourselves in that orbit. And that's where the mission life comes from. So we have to use our thrusters to keep ourselves in that orbit. We have other systems that can handle that momentum change too. But eventually the fuel runs out trying to keep ourselves in that orbit, and then things deteriorate. But yeah, about every 3 weeks we have to do a maneuver to keep ourselves out where we want at L2.
Awesome.
Thank you.
We have a question from Peter McGrain.
Yeah. Can you talk a little bit more about the how the bird is powered and about those thrusters and the fuel that's on board? Do you have I think you mentioned solar, but are there other avenues of power on board as well?
Sure. So two different, I guess, categories of power. So one is the solar array, and so the beneficial and I guess I would say simple thing about being at L2, like I mentioned, and if you remember from that picture, that it doesn't have the solar array listed correctly. It's this thing right here. It comes off at a diagonal angle from the spacecraft bus. Again, like I said about the orbit, it's always got the sun in a predictable location. So we have full power on the solar array at all times. And in the comparison to something in low Earth orbit, you have sun for half the orbit, and then the other half of the orbit, you're draining the batteries. So you're always kind of charging and recharging the batteries. But that's not the case for Webb. We're always in full sun. So we actually don't expect to use the battery much at all. It's there almost as a backup, and we use it during launch. So the other thing you mentioned is propulsion. So we need to fire the thrusters to get to our orbit. We call that a mid-course correction maneuver, and that gives us enough delta velocity to get out to L2 in the first place. We also use thrusters to, like I said, keep us in the L2 orbit, doing station keeping maneuvers. So that's the one, the fuel on board, that's the one that's not replenishable, right? Solar power is replenishable and it's constant and it's predictable, but fuel on board is non-renewable. So that's the one that's going to eventually limit the mission life. But we do everything we can. That being said, we do everything we can to minimize fuel usage. We have another interesting technology that's called reaction wheels, and so those can control the orbit. It's an electrical device by kind of counter spinning. So whichever axis you want to spin the spacecraft in, those spin the opposite way, and they're redundant in all three dimensions. But eventually, we do have to use fuel to kind of counteract that momentum. So hopefully that answers your question.
Yeah, that's great.
Let's see. We have a question here. How far in advance of launch do you need to get it down to Kourou?
So it varies by project. This project, I think, goes down there about a few months before launch, and there's a lot of processing that happens down there to get it. It's from the spacecraft perspective, it's ready to go, but the launch processing facility needs time. They pick it up on a crane, they put it on top of the rocket, they do all the checkouts. So it only needs a few months down there, and it travels by boat. A lot of people ask this too. It lives in Redondo Beach, California right now. It'll go from the port of Los Angeles by boat down in the Pacific Ocean. It'll cross through the Panama Canal to the Atlantic, and then it'll make its way to the launch site in French Guiana.
Has it ever been considered to use drone technology for onboard repairs or work?
I think so. What the question might be referring to is there's I guess a proposal right now to be able to fix spacecraft that are old or maybe out of fuel and refuel them that are closer to the Earth. It was not really considered for us because, again, we're so far away from the Earth. I think that's more of a realistic proposal for things that are in low Earth orbit, again, where the astronauts in the space station are, and maybe medium Earth orbit, where like the GPS constellation is, but not out at L2. I don't think it's feasible at this point.
What what instruments are on board, and how will it communicate findings back to Earth?
Oh, so you're asking a science question. I told you guys not to do that. So there are, let's see, the mid-infrared instrument. There's a near spectroscopy. Basically, the gist of it is that they're separating various wavelengths of light into their components, and then the instruments inside the back of the telescope there are breaking it down and analyzing it. They also have micro shutters that can let in only certain parts of the sky that are showing light, so they can kind of characterize what they're looking at. There's 4 science instruments on board: NIRI, NIRSPEC, NIRIS, and why am I blanking on the last one? 4 science instruments in any case, and those will accomplish the mission.
And for communicating the findings?
So we have high data rate. We have 28, well, high relatively speaking, 28 megabits per second. We use a Ka band link. We also have an S band link, and really those are just shorthand for the frequencies that those signals are sent in. So we have redundant radios on both S band and Ka band, and those are sending data down. And we also are able to command on S band to get ourselves into any out of any anomaly, or to do the normal operations flow, the deployments, that type of thing.
What's the time delay?
Light time delay it's on the order of several seconds one way. Yeah, so so by comparison, the Voyager, which is outside the solar system, is I think about a 19-hour one-way light time. Ours is nowhere near that. So it gives you a sort of comparison of how far away Voyager is.
Let's see, we have another question from my dad.
Oh, yeah, thanks. Hey, Tom, I'm gonna save you from a science question and steer towards something that I think would be probably pretty close to your heart. And given that the title of this series of webinars is Domers in STEM, I want to ask you a question about the skills gap. I mean, you're an engineer. You spent a lot of years studying, and you've got 2 boys. You know, this country is in dire straits when it comes to the skills gap in engineering, not just for people like Northrop or NASA, but any manufacturer, from a mom and pop machine shop, right up to Boeing. And the predictions for the next 20 years are dire. What, for example, your boys do you talk to them about STEM stuff and trying to get them interested in that? And what at Northrop are people doing to try and get more young people interested in science, technology, engineering, and math?
Sure. So it's a boy and a girl, a 4-year-old and a 2-year-old. So I think for me, it was always kind of pursuing and fostering a natural curiosity. I mean, anyone with kids knows right away that it doesn't take a lot to kind of pique their interest. Playing with their own feet when they're real young is enough to keep them busy for a while. So things like that, just fostering that and never getting in the way of that was something that was really kind of beneficial for me. Something that Northrop does that's actually happened fairly recently in the last few years, or several years, I'll say, is they where I used to live in California, they created call it a fab lab, or fabrication laboratory. So like a maker space, right? 3D printers and machine shop components and the accompanying classes and instruction to go with that, to show people how to make things, how to be creative. I recently got I should have owned it sooner, but I recently got a Raspberry Pi for the first time. So, you realize that the only limits are your own imagination. Like the even basic technology, like your smartphone can do pretty much whatever you can dream it to do or program it to do. So I would say just fostering that curiosity is what I would personally like to impart in them. And the other thing, just to go back to my own background, what I've found without fail in engineering is questioning assumptions and speaking up when you see something that doesn't make sense, and doing that without any fear of judgment or hurt feelings or anything like that. I mean, those are the things that lead to mission success. No one's going to get offended if you find a problem that would have caused a major issue. So being skeptical, asking hard questions, and I mean, they take it upon themselves to seek the answers, right? There's no one preventing them from doing that, and that's what I tell students at Notre Dame today, to pursue is ask hard questions and go seek the answers. No one at any level of management or engineering is going to get in your way if you're trying to solve hard problems. And I mean, that's looked upon with a lot of respect. So I hope that I can foster that in my kids and spread that message. So thanks for the question.
All right. Anyone else have any questions?
Hey, Tom, this is Rachel. How many single points of failure on this system, and how long from launch until it deploys?
Okay, so single point failures, that's a good quiz question. We have it all documented everywhere. I mean, there are probably maybe a few dozen, and they're all handled either operationally. We have procedures to kind of work around them, or they're more scrupulous during the manufacturing and transportation process. So they're taken with great care. And I'm sorry, I think the other question was how long from launch until deployment or until science. So it's about 30 days that we take to, we call it commissioning, to commission the engineering side of things. And then another roughly 5 months of science calibrations and checkouts and data analysis. So from launch till the time it's doing science and accomplishing, starting the mission is about 6 months.
Got another question here. Who will be able to use the satellite, and how do they get access?
So scientists from around the world will use the data, and there's been a proposal subsystem, or a proposal planning system, I'm sorry, that has been stood up, and that's basically to take proposals from astrophysicists, scientists around the world, anyone who has a potential need or a potential experiment that JWST could study and contribute to, can write it up and write what they propose to do. And then it goes through a series of approvals and reviews, peer reviews and approvals by project scientists and managers and everything. And then it will eventually, sorry, my computer's going to go to sleep here. And then it will eventually, as it's cleared, it will get time on the observatory in an order of priority. The other thing that's slightly different about this mission than Hubble is it's really centered around the science. So everything centers around the science. So the time that or how often we can point the antenna in order to communicate back with Earth is dictated by whether or not science is being taken. So if they're in the middle of a critical observation, we might miss a contact with the ground, that type of thing. So science is the overwhelming priority on this mission, which is the right way to go, in my opinion.
Another question for my dad.
Oh, no, sorry, I forgot to lower my hand.
Oh, okay. Anyone else? Peter McCran?
Yeah, Tom, so you mentioned that there's a kind of priority to the science projects, and I maybe this is too on the science side for you, but is there certain high profile projects that are already planned to be, you know, first priority, second priority after the 6 months of commissioning? And I guess how much of your 5-year or 10-year plan is already kind of planned out for the science observations?
So I don't know specifically how much of it is planned, but I can tell you the early time frame, maybe a certain number of weeks or months are, I mean, they're already set in stone at this point. I talked to a couple scientists, and they're essentially at the point where they have a discovery that they think they're ready to make, and they're waiting to fill in, you know, the values and the images, right? So they're so well prepared, and they know, I mean, they've known for a long time what Webb can do and what data it's going to return. So that stuff is high priority, and then it'll start to go into a revolving door of you know, priority and whatever else gets submitted. So, but a lot of it is front loaded to, you know, high priority science discoveries that are, I don't want to say low hanging fruit. I'm probably selling it short, but from a science perspective, they're just ripe for discovery.
Gotcha. Thanks.
Now, is that a raised hand, or did you forget to lower it, Dad? Because I thought I lowered the hand for you there.
Thought I lowered it. Sorry.
Why is it a 5-layer sun shield?
So no, good question. I should have talked to this. So usually what I say is, yeah, why not 4 or why not 6? Well, I mean, it's a design trade, right? As with every other inch of the spacecraft, it's a trade-off between weight and what it can do, right? So if we had 6 layers, yeah, I would get, you know, more temperature delta, which is good, but then it would be heavier, which is bad, which costs us, you know, money and fuel on the launch vehicle, that type of thing. So everything is a design trade, and 5 ended up being the optimal solution with what we're working with.
All right. Any last minute questions here before we close the floor?
I just want to say thank you. If I don't get another opportunity, I really appreciate it, Christoph and everyone. Great questions. Glad to have the opportunity to share what I do, and look for us in the news, hopefully October, and should be seeing some great images, not unlike Hubble, hopefully before too long. So thanks.
Awesome. Thank you so much, Tom. And thank you everyone for sharing or spending your time with us on this Thursday evening. You know, we have not as many events as we used to in the past due to, you know, the limitations with COVID and everyone having to do virtual. I'm sure everyone's a little bit tired of all the Zoom meetings and whatnot. But please stay tuned to the Notre Dame social media and emails, the newsletter, Notre Dame DC. We have some events planned, one of which is a health and wellness event next month. We're still finalizing the speaker docket for that, but more information will come. And lastly, I just want to plug real quick, if you're not yet a member of the Notre Dame DC Club, please consider joining. Your membership dues not only support the events that we do every year, but a lot of it actually goes to the scholarship fund that helps local area students from the DC area get some financial assistance for their Notre Dame education. I myself was a recipient of this scholarship in my time at Notre Dame, so I can attest to the fact that it really helps. And yeah, so please consider that. Our website is ndedc.org. And let's see, Tom, do you have the link for that YouTube video? Actually, I don't think you sent it over to me. Send it to everyone.
Sure. Maybe I can put it in the chat, I think.
Yeah, it's about a 5-minute long video, but it's really cool. So definitely check it out.
Sorry, it's taking me a second here.
No worries. All right, there it is, everyone. Be sure to click on it, copy paste, save it somewhere, and watch it later on. All right. Well, that should be it. Thank you again, Tom, for your time and all the fun science and engineering stuff that we've learned today. I mean, that was really cool. Looking forward to a successful launch and deployment in the future.
Yeah, thank you. Thanks, everyone.
And and one last thing, Tom, we did discuss that we will be doing another event closer to launch, hopefully with a little more finalized information on how everything's going to go on that end. Closer we are. So
sure, yeah, I'd be happy to. And also feel free. I mean, if anyone has other questions or interested in talking more about the aerospace industry, the space industry, feel free. I left my email address with Christoph. Feel free to reach out directly if you'd like to.
All right. Well, that's it for tonight. Thank you again. Hope everyone has a great evening.
All right. You too. Bye.
Thank you.